Welcome, everybody. Thank you for choosing to take this class of Fireground Hydraulics. My name is Colby Davis. Uh, Hope to bring something new to you in this class that maybe you've never seen before, as the experienced operators, things that maybe you've forgotten, or as the officers that are training the newer generation, we're fine tuning some things so that you can get them on their way the appropriate foot. If you have any questions at any point, pause this. Um, you can email me. You can call me if you'd like. Facebook, whatever you have access to, and we'll work through it together. On the calculations, I will have a short session where you can pause, work your calculations, and then restart the video so that you can uh, fully understand everything that you're doing. So let's go ahead and get started. As a disclaimer, this course was specifically designed to help all individuals with pump operations, from the new drivers to the seasoned driver looking for a refresher to a company officer training drivers and looking to freshen up on their own knowledge. Again, it's all about continual growth, continual learning, and refreshing up on everything that we do. You will not receive Pro Board certification for this course, nor a state certification, but you will receive valuable knowledge that will hopefully stay for a lifetime and be something that you can pass down to your next generation firemen. This course will give you a better understanding of pumps, pump operations, and calculations that are much needed to provide the appropriate amount of water to personnel on our fire scenes. So I really like this picture. I have no clue where it came from. It's one of those things I found on Facebook or maybe on Google, I can't remember. But it represents someone who can drive an apparatus that doesn't understand the pump, doesn't understand calculations, and doesn't understand their job as a driver operator. No matter how much hose you carry around, you can stretch it, but can you supply it? Can you give the crews at the end of the nozzle the pressures that they need correctly and the correct amount of water that they need to go for the fight that they're going for? Some NFPA standards. We'll go more in depth in the next couple slides, but this is a highlight of them. NFPA 1002 is our standard for fire apparatus driver operator, the professional qualifications. NFPA 1901 is a standard for automotive fire apparatus. 1911 is our standard for the inspection, maintenance, testing, and retirement of in-service emergency vehicles. And NFPA 1410 is our standard on training for emergency scene operations. So our NFPA 1002, just like any other standard we have, NFPA 1001 for firefighter, our 1021 for our officers, 1041 for instructor, so forth and so on. This is what's going to say, hey, you have to meet this standard for whatever the apparatus is to be able to operate it appropriately. For this class specifically, we're only going to worry about chapters 5, 6, and 10. So 5 is your apparatus that are equipped with a pump. That could be your quints, your engines. Chapter 6 is apparatus equipped with an aerial. We're not so much going to go in detail about that, but I wanted to let people know that Chapter 6, if you decide to go further with aerial operations, Chapter 6 is where you would find all your standards that you have to meet. And Chapter 10, your mobile water supply apparatus. That's going to be your tenders. In 1002, we have 1.1. That's our scope. This standard identifies the minimum job performance requirements for emergency response personnel who drive and operate fire apparatus. So this is, again, just setting a minimum standard for you. If your organization decides, hey, we're going to go further or deeper with more knowledge, more skills, more drive time, whatever it may be, that's on them. And honestly, would benefit you more so than trying to pencil whip and do less. So this is just going to be your minimum standards. NFPA 1901, again, our standard for automotive fire apparatus. 1.1 is scope. This standard defines the requirements for new automotive fire apparatus and trailers designed to be used under emergency conditions to transport personnel and equipment and to support the suppression of fires and mitigation of other hazardous situations. So, within this standard, again, this is if we're retrofitting an apparatus, you do have to meet this standard. If you're building a new apparatus, you will have to meet this standard. This is where it states that engines have to have a minimum of 300 gallons of water on them. You have to have a minimum pump capacity of 750 GPMs. Our seatbelt alarms that ding if we're not wearing our belts, which we should be, this is what sets that standard. It says, hey, it has to be integrated. Our VDR, that's our black box. That's why the picture on the right's there. That's our vehicle data recorder. It determines, how fast you were going, when you accelerated, when you braked, how much pressure was put on your brakes, if you were wearing your seatbelt, the whole gamut. So whenever an accident occurs, this is what they look at to determine everything about the situation. And then further into that is the minimum equipment that each apparatus has to have on it. NFPA 1911, that's your standard for inspection, maintenance, testing, and retirement of in-service emergency vehicles. Again, the scope, the standard defines the minimum requirements for establishing an inspection, maintenance, and testing program for in-service emergency vehicles. And this says we have to have them pump tested yearly. They have to pass the pump test to stay in service. NFPA 1410. So these are going to be more of our training requirements. Some organizations may have this in play right now as far as yearly for their yearly research or yearly competency for their organizations. But the chapters that are more for this class are Chapter 8, Chapter 9, and Chapter 10. 8 being required performance for hand lines, 9 performance for master streams, and 10 performance for automatic sprinkler system support. Some examples of these, that way if somebody doesn't know what the NFPA 1410 is, you may say, hey, we do those. I didn't know that's what it was called. So you have a 300-foot supply line that you as an operator have to lay out. Deploy a hand line flowing a minimum of 100 GPMs. Establish a water supply and charge your backup line, which has to be a minimum of 200 GPMs. And you have to do that within 3 minutes. The other one, 300 feet of supply line, 100 feet of hose supplied to the sprinkler FDC, and pumped at 150 PSI. All that has to be set up and flowing correct pressures at 3.5 minutes. Again, this for driver operator programs or recertification competency, however you want to finagle it. NFPA 1410 does set a standard of things that you as an operator have to meet time-wise and be able to accomplish. Our pump capacities. So how do they figure these? We've all seen this little chart on the left. This is a Pierce that we have in my department. We've all seen this chart, and some may wonder, hey, what does it mean? Well, it's our pump capacity. So as you can see, it says 1003 GPM, 150 PSI, 704 GPM, 200 PSI, 501 GPMs at 250 PSI. Well, when they perform the pump test, they perform it on draft. Anybody can flow from a hydrant. All you are at some points, if the hydrant's good enough, you are a manifold, pulling levers and letting pressures go as needed. So to make sure that your apparatus can perform what it's supposed to, it can pull a draft. They perform it in a dump tank. You see them earlier in the NFPA 1911 slide where it has a trailer full of water. They're drafting out of it and dumping it back into that trailer. To pass a pump test, it has to be able to provide 100% capacity of that pump at 150 PSI. So this one has to produce 1,003 GPMs at 150 psi. It has to provide 70% capacity at 200 psi and 50% capacity at 250 psi. So some of you may say, hey, why, if there's more pressure, shouldn't it be putting out more water? Not necessarily, because your pump is spinning faster, therefore it's not collecting as much water as it would be and sending it out the discharge. Now let's swap over from the draft side of things with our pump capacity test. That doesn't mean that you can only pump 1,003 GPMs at 150 psi. If you are hooked up to a hydrant that's giving you 2,000 GPMs, if you have the orifices on that apparatus, you can put 2,000 GPMs out of it. As you can see, that last statement, your capacity is based on the 2.5 discharges on the apparatus. So you get 250 GPMs per 2.5 discharge on the apparatus. Types of pumps. So this is your centrifugal pump. Some people call it centrifugal. I've always, since forever, called it a centrifugal pump. We may have seen this diagram on the left. This is our normal picture that we do get. I do like it to show the different parts. However, it kind of psychologically messes with you and makes you think, well, how does the water get in there? Does it just go into the big impeller? But then it looks like it's closed in. So that's why I did this cutout on the right side. As you can see right here, there is a coupling, or the eye sticks out. Sorry, not a coupling, but the eye sticks out right here and allows water to go into the true eye. So the one on the right side has a notch where the piping comes in and water actually goes into the eye, and then it goes into the impeller and the out of the vanes. Okay, so I feel like this picture on the right was a true better picture than the one on the left. It can help you understand that water comes in through the piping into the eye, which is the center of those impeller, and then the vanes are what is going to rotate it around and push it out the discharge. Some of these pictures, I could not find a good picture of some items on here, so please don't make fun of the drawings that I made. This is one of them. It took quite some time. But a second type of pump is our positive displacement pump. So our centrifugal pumps are going to be more our main pumps. A lot of, if you have a normal apparatus that's not a rear pump or a front bumper pump, then you're going to have a centrifugal pump. Our positive displacement pumps, these are going to be more of our primer pumps, our rotary vane pumps, and they're going to be able to pump air. That's one issue with the centrifugal pump, is it doesn't have the ability to pump air. So we put a positive displacement pump on here. It has the ability to pump the air out of the centrifugal pump, therefore bringing water into our pump and discharging it. How this works is the vanes, if you look at the top, they're more flush with the casing itself. As it rotates to the left, air or water, whichever it's pumping, follows the arrows and has the ability to come out of the other side of the pump. The vanes are going to extend and create your seal and have a continual seal. So as it rotates left counterclockwise, the vanes are going to drop in to keep that seal, and then they're going to rise up as it meets the resistance and pushes either your water or your air out. This is going to be hooked to a valve, a diaphragm that's actually on top of your centrifugal pump. It's going to, when it starts pulling, it's going to raise the diaphragm on the pump up. It's going to let the air out. It's going to expel it, and then it's going to decrease the pressure inside your centrifugal pump to meet its needs to pull your draft. So it's going to decrease below atmospheric pressure. That's what we have to do to be able to pull a draft, is get below atmospheric pressure. Our single action, as you push the opposite direction, your intake is going to close and you're going to discharge that water, but only that water. Now, with your dual action pumps, you have both directions. It's going to pull water and push water. If you look at this picture, on the right, you can see the intake is closed and the discharge is open. We're pushing that water out that discharge. But on the left side, our intake is open, our discharge is closed, and now we're pulling water in so that whenever we reverse our push of the pump, we can reverse all of our action and still discharge water again. So now with this pump versus a single action pump, you're actually going to get twice as much water. So this is our opposite side, where now we are pulling and we're still going to discharge the water that we just filled with. Our intake on the right side is open, our discharge is closed, and now we're discharging out the other side. A lot of places specifically spec out two-stage pumps, and a lot of people don't really understand them. So that's one reason I added all this, these different types of pumps in here, is so that people would understand no matter where they went to. Maybe you get a new apparatus. A lot of these volunteer organizations buy apparatus that are, they find. So if you do find a two-stage pump, or your organization specs them out this way, hopefully this will help you understand it a little more. So to provide water, you have two different ways. You have a pressure series and a volume parallel. The best way for myself to remember this, pressure series, is you're going from series 1 to series 2. So you're going to go from one pump to the second pump, out the discharge. Volume parallel being they're pumping at the same time. So now your water is going to come from your intake. It's going to go to both pumps, and it's going to discharge together. There's not going to be a series. So they discharge together. Now, just like our single action and dual action pumps, in volume parallel, they're pumping together. They're pumping double the volume. You're going to have a transfer valve. That's the picture on the left there. That's going to put it in pressure mode or series mode and volume parallel mode. So you have to make sure as well that you're in the right mode for the operation that you're going to do. On the right is pretty much the only picture that I could find of a two-stage pump. I wasn't even going to attempt to try to draw one of these, but this is a pressure series mode. So if you notice, your water comes in your intake and immediately goes right into the first pump. So above that first pump is going to be your transfer valve that's going to say, hey, we're going to discharge this water, or we're going to send it to the second pump. We're going to increase the pressure and we're going to boost it out. So because this is in pressure mode, it's going to go in your first pump. It's going to go over to the second pump, and then it's going to be sent out the discharges. And I could not find a picture of it being in volume parallel mode. If it is in volume parallel mode, water is going to divert left and right of your intake. So your intake's on your left side, it's going to divert left and right in your intake. And water is going to go in both sides of your pump. And then it will just both discharge straight out into your discharges here. So again, know that pressure series is you're building pressure. You're putting it in a series. Pump 1, pump 2, boost the pressure, sends it out. Volume parallel, they're pumping together. They're adding more volume. And they're side by side pumping water out the discharges. Our relief valves, so our TPMs versus our pressure governors. Again, some of this is going to be personal based. I prefer to have a TPM. As we all know, computers have capabilities of messing up, and in a hand spun wheel or a pull valve, the only thing that's going to happen to those is something's going to break, something that we can fix. Maybe, if you're mechanically inclined and you have the capabilities of fixing it right now, while we probably shouldn't put non-shear pins in these, you could potentially put a piece of metal in there that's going to make it work for now. I'm not condoning that, but sometimes you got to make things work, especially if you have guys inside that need some relief on your pressure, and you can't provide that at the moment. So with that, our TPM is on the left. Our pressure governor is going to be on our right. Our TPM is between the intake side and the discharge side of the pump, and it's continuously monitoring and measuring those pressures. So if the discharge overrides what it's supposed to, then it's going to dump that water back into the intake side to relieve that pressure from your people. So if you shut down a line, even though maybe it's 100 GPMs and its pressure is lower than the other line, you're still trying to force that water out another discharge. It's still coming in your pump. So what it's going to do is it's going to divert that back into the intake side. Your pressure governor is on the discharge side and only throttles the engine based on discharge pressure and where the governor's set. Majority of the time, these are slower to react than your TPM. Your TPM, you may get that initial surge, especially if somebody water hammers something. You may get that initial surge, but it's going to stop. It's going to find a way to dump the water, whether it's the intake or on the ground. It's going to find somewhere for that water to go. Your pressure governor is going to allow them to somewhat get beat up, and then it's going to decrease your engine throttle and level off. Another thing that it does is if you have multiple lines that are different pressures, when it drops your engine RPMs, you're also dropping your pressure of those other lines that are discharging. So that's what you have to be careful of. Now with our TPMs, so on the right is a diagram of our TPM. We'll get into exercising these when we talk about maintenance. But your spin wheel, your hand wheel, as you can see there, is going to have your adjusting screw and your spring that it's going to set and allow you to set the pressure correctly as to when you want this water to divert, dump, not be on the other line that your people are on. On the left is an electronic throttle. Don't confuse this with a pressure governor, which is on the right. On the left is an electric throttle. Some probably have seen the older throttles that has the big red button, the knob, and the wire on the back, and that's what's going to increase your pressure. These are going to be electronically driven. As you can see as well, you have your idle button in the center of that throttle, same as you have idle on your pressure governor. be sure not to just hit that when it's revved up as high as you may have it pumping. If you're still using 1 3/4 hose with the 15.5, of course we'll go over these coefficients later, but with the 15.5 coefficients, you're going to have higher pump pressures than, let's say, 7/8 hose that may have 6.59. So try not to have high pressures discharging and then walk up and just push the idle button. That could be damaging to the motor and to your pump. Formulas. So we'll start off very generic and get a little more in depth. But for our PDP, so this is our pump discharge pressure. This is what is going to be our highest line when we're pumping. If you're pumping multiple lines, then you're going to have to pump to your highest line, gate back your other discharges as needed. Always, always, always start with your nozzle pressure. So as you start these calculations, always figure out, hey, I have a smoothbore, I have a fog nozzle, whatever it is, 50 psi, 100 psi, master stream 80 psi. Write that down. Go ahead and write that down. Then we're going to calculate our friction loss. So then we'll add our friction loss. Then we'll add our elevation loss, and then our appliance loss. If for some reason you don't know your GPMs, this is more going to be on your smoothbore tips. The formula is 29.7 times your diameter squared times the square root of your nozzle pressure. One thing in my organization, we always try to pride ourselves in knowing, hey, this nozzle gives you this GPM. This tip, this master stream gives you this. We know what we could face, how many GPMs we could be putting out. So, I'll have a chart. We'll go over it in a second. But this is your basic formula for that. So our friction loss formula. So we start off with our nozzle pressure. Now we go to our friction loss. If you look on the bottom, you have quantity squared over 100 or Q squared. That's still going to equal Q over 100 squared. So when you're doing your math problems or you're teaching somebody how to do the math problems, let them understand that all three of those are the same. They need to put their quantity over 100 first, and then they're going to square that number. Because if they try to square their quantity and then divide it by 100, which is how the equation on the left is written and how it's always been done, but it wasn't ever meant that way. It was always meant like the one on the right, parentheses, quantity, or Q over 100 squared. That's going to give you your appropriate number to do your calculations. So when you're writing it out, you can, as you can see up top, your C, that's going to be your coefficient, and we'll have this chart in just a second, times our quantity squared or quantity over 100 squared, and times our length of hose over 100. Our elevation loss, or our head pressure, to figure this, we use 0.434 times the height in feet. With this, a lot of people do try to do quick math, and that's absolutely fine. It's not that big of a difference, but the correct way to provide this is 0.434 times your height in feet. NFF or RFF, that's going to be our needed fire flow or required fire flow for a building. To get this, we're going to do the formula length times width of the building divided by 3 times our percentage of involvement. So if you have a 50% involved 2,000 square foot building, then you need 1,000 GPMs to appropriately extinguish the fire. times the number of floors that are involved. So 1-story building, obviously the same. 2-story building, 2,000 GPMs. Our head pressure, that's going to be for our sprinkler activations. We're not really going to worry about that too much as far as like elevated water tanks. We don't really care about figuring those. Does it have water in the elevated tank? Is the sprinkler activated? Okay, we need to be stretching lines from our standpipe or our flying standpipes or dragging hose up the side of the structure and making our way to the seat of fire with hand lines. But for head pressure, and we'll have a couple of one equation on here, you'll figure it 0.434 times your height in feet. Constants, things you will know. If you want, by all means, take a picture of these. I have sent these charts out to people previously, and I will be more than happy to send this out for you. That way you can have it for yourself, for people you teach, maybe for your organization if you want to kind of drive it that way to have a set standard. But these are the charts that what I talked about, priding ourselves in what we do know. This is one of those charts. For this class, and right in this moment in time, I want to talk about our nozzle pressures, but later we'll get to talking about understanding your apparatus. So for this class, and for any equations in this class, I want you to use the chart on the left. So our fog, whether it's a hand line or a master stream, we're going to use 100 psi. For a smooth bore hand line, we're going to use 50 psi. And for a smooth bore master stream, we're going to use 80 psi. On our hand line, these green charts are going to be, except for the bottom two, are going to be our smooth bore tips. 1/2 inch tip is going to give you 52 GPMs on a hand line. 3/4 is going to give you 118 GPMs. A 7/8 tip is going to give you 161. 15/16 184. A 1 inch 210. 1 1/8 266. 1 1/4 328. And our fog nozzles can vary from 95 GPMs to possibly 300 GPMs. Our master stream tips, 1 1/4. So because of how our calculations are with our nozzle pressures, now we've increased to master stream. It's 80 psi nozzle pressure. When we put it into our GPM formula, that's why 1 1/4 on the hand line is not the same as 1 1/4 on the master stream. So we've increased from 328 to 415. 1 3/8 is going to give you 502 GPMs. 1 1/2 is going to give you 598 GPMs. 1 3/4 is going to give you 813. 1 7/8 934. 2 inch 1062. 2 1/2 1659. And our fogs can give you anywhere but 350 to, it depends on if you have something like a Terminator, your high flow nozzles, it can give you 1,000 GPMs. Our coefficients, again, some constants that we need to know. For 1 inch hose, 150. These are not PSI, these are not GPMs, these are specifically just a constant and a coefficient. 1 1/2 is 24. 1 3/4 15.5. 1 7/8 6.59. 2 1/2 is going to be 2. 3 inch 0.8. 4 inch 0.2. And 5 inch 0.08. On the right side, you have the chart of 3. These are going to be multiple lines. So if you're flowing a Siamese, a FDC, an apparatus, then you can use this formula. So if you have two 2.5 inch hose lines, you're going to have a coefficient of 0.5. If you have 3 of them, it's going to be 0.22. And our typical, if you have 2 3-inch lines supplying, a ladder, relay pump and an engine, or supplying your portable monitor or FDC, the coefficient is going to be 0.2. When using multiple lines, there's 2 ways to calculate this friction loss. You can either use the coefficient for multiple lines, which is the chart on the right, or divide the flow by the number of supply lines and use the original coefficient. So 3-inch hose, if we were using 1,000 GPMs and you wanted to use the coefficient for multiple lines, you would do 1,000 GPMs and your coefficient would be 0.2. If you were going to use the single line coefficient, it would be 500 GPMs instead of 1,000. It would be 500 GPMs and 0.8 as your coefficient. Again, we're going to have some math problems where we will do this. Your elevation loss, again, you have your 0.434, and that's per foot. 1 pound of water, or 1 psi, raises water 2.3 feet. That'll be significant when we get into our drafting operations. And then we need to know the atmospheric pressure is 14.7. Again, we're trying to overcome this, and that's what's going to, bring water into our pump. Our appliance loss is going to be figured at when you have more than 350 GPMs. So our small appliances, Siamese, Wise, maybe even a portable hydrant or manifold as some people call it. I've always called it a portable hydrant. Those are going to be your small appliances. That's going to be 10 psi that you add to it. Your large, it's going to be your apparatus or your FDCs. You're going to add 25 psi to it. Now, don't get stuck in, well, my organization says under 350 GPMs, we add 5 psi for small appliances. If that's what they say, by all means, add that 5 psi. On your standpipe systems, you will always add 25 psi. Even if you're only flowing 266 GPMs, you will always just add the 25 psi as the appliance loss. Square roots that you may need to know, that way you can pop off as you're trying to figure calculations. As maybe you have it on your phone and you want to make sure you have your right pressures. You grab your phone real quick and plug in square roots. Obviously 100 is 10. For 50, our square root is going to be 7.07, and 80, our square root is going to be 8.94. Our squares, so again, you're plugging calculations in. You're wanting to make sure that you are right. 1 inch is going to be 1 inch and 1/8 tip, 1.26, inch and 1/4, 1.56, inch and 3/8, 1.89, inch and 1/2, 2.25, inch and 3/4, 3.06, 2 inch is going to be 4, 2 1/4, 5.06, and 2 1/2 is going to be 6.25. At this point, if you need to take pictures or go back and take other pictures of our constants, whether it's our GPMs or our coefficients, go back and take those pictures, because we're about to get into some calculations, and it will just help you have these in front of you. Our hand method. These are what we're going to use in the middle of the night if we don't know our apparatus like we should, or they're stretching lines that we haven't figured. We're making new lines we're going to take this method and we're going to use it to the best of our ability, and this is how you understand it. So for 1 3/4 hose, you're always going to use your left hand. You notice on the tips of the fingers you have constants 1, 2, 3, 4, 5. Above those you have 100, 125, 150, 175, 200. That's your GPMs you're flowing. Okay, so, and then in the middle, in the palm, you have a 10. That's going to be the coefficient that you multiply by. So, if we're flowing 150 GPMs on an 1 3/4 hose line, it's 100 feet. Then we're going to multiply 3 times 10. It's going to give us 30. So these constants, the 1, 2, 3, 4, 5 multiplied times the 10, are for a 100-foot section of hose. So we have, for a 100-foot of hose, 1 3/4, flowing 150 GPMs, we're going to have a friction loss of 30. 200 feet is going to give us 60, because it's going to be, our 150 gives us 3. 3 times 10 is 30, and that's for 100 feet. We now have 200 feet. 30 times 2, 60. For our 2.5 inch hose, this one gets a little confusing. It took me quite a while to not wrap my head around it, but force it into my head and say, hey, this is how it works. So you have your constants on your fingers, and you have constants between your fingers. So each finger is going to be an even number. Each gap is going to be an odd number. Our GPM above those fingers are going to increase in 50 GPM increments. So from 100 to 500 in 50 GPM increments. So let's take a 2.5 inch hose line. Again, this is for 100 feet, just like it was for the 1 3/4 hose line. This is for a 100-foot section of hose. So, say we're flowing 300 GPMs. What we're going to do is, we're going to take the first number of each GPM, so 3, multiply it times the constant that it's with, so 6, and it's going to give us a friction loss of 18 per 100-foot section of hose. If we have 300, we're going to do 300 feet, 300 GPMs. We're going to do 3 times 6 is going to give us 18. 18 times 3 is going to give us 54. So we'd have a friction loss of 54. Our condensed Q method, this is going to be for our supply hose. Again, Q squared is the same thing as quantity over 100 squared. For 3-inch hose, it's going to be exactly that, Q squared, quantity over 100 squared. For our 4-inch hose, it's going to be quantity over 100 squared, all of that divided by 5. And then 5-inch hose, quantity over 100 squared, that answer divided by 15. This is what's going to give you your friction loss in your 3-inch, 4-inch, and 5-inch supply hose. So piping in the apparatus. We all know that there's pumps in there, there's wires in there, there's obviously the piping itself. So with that, it's probably not just going to have a straight line. Understanding how your piping is inside is directly correlated to your pump pressures. The only true way to figure correct pump pressures is know how much friction loss there is in your piping system. So you have your gauges on your pump panel. You would take a gauge and put it on your discharge. Then you could take a gauge and put it right before your nozzle, and then you would use your pitot gauge to figure out how many GPMs you're flowing, what your numbers should be, and then you would check your 3 gauges to ensure that your pressures are exactly what they're supposed to be. NFPA 1901, we talked about the standard earlier that says, hey, this is the set standard for renewing apparatus or building new apparatus. It states that all piping must be constructed of corrosion-resistant material and be able to withstand 500 psi hydrostatic testing. In the standard, it says that your piping has to be able to hold 100 psi more than your pump can provide. So if you notice on our gauges, on our master intake and our master discharge gauges, they read 400 psi. So 100 more than that is obviously our 500 psi. Two lines. It doesn't matter in this instance which one you figure. Figure them both, and then you're going to pump to your highest line and gate your other one down. So, our first one, 200 feet, 1 3/4 hose, smooth bore with a 1-inch tip. Well, we just did that one, right? So, we know how to perform those calculations. If you want to, pause this and do those calculations real quick, and then we'll get into the next hose line. Our second one. So, our nozzle pressure, it's a fog nozzle. So it's going to be 100 psi. For our friction loss, 1 3/4 hose again. So we'll have 15.5 times. It gives us our GPMs. And you'll see on some pictures that I have in just a little bit, our fog nozzles give us the GPMs that we flow. Smooth bores are actually starting to get where they have diagrams on the side of the smooth bores that they may give you as well. But these give you your GPMs. So our GPM is 175, so over 100 squared. And then times our length of hose, 150 feet, over 100. And that's going to give us a friction loss of 71. So, for the top line, we have a pump pressure of 186. And on the bottom line, we have a pump pressure of 171. Our total PDP, again, is going to be our highest line. So 186 psi is going to be our total discharge pressure. You will have on your master discharge, you should have close to that pressure. Sometimes when we have lower pump discharge pressures and high intake pressures, it will vary. Do not base your entire operation off that master discharge, the big discharge up top. When you're pumping lines, make sure that you are paying attention to the gauge that is specifically on that discharge. You can use it to help you set your TPMs. On your pressure governors, there are ways that you can go in there and set. It's very difficult, but there are ways that you can go in there and set your relief valves. But obviously it's not as easy as the TPMs. So, total pump discharge pressure for this one, 186. We'll have the pump going at 186 psi, and we're going to gate back our fog nozzle line with our spin wheels or pull valves, whichever one you have. With this example, we'll have a skid load. We'll have 100 feet, 3-inch supply hose to a gated Y, 150 feet, 1 3/4 hose, fog nozzle, 175 GPMs, and a 200 foot of 2.5 hose, smooth bore, 1 1/4 tip. We'll start with the Top line on the skid load, 150 feet, 1.75" hose, fog, 175 GPM. So we know that it's 100 GPM or 100 PSI nozzle. So start there, 100 PSI. Plus now we got to figure our friction loss. Our friction loss is going to be 1.75", 15.5 times 175 over 100 squared times 150 feet divided by 100. That'll give us friction loss of 71 and a pump pressure of 171. Second line, 200 feet, 2.5, smooth bore with an 1.25" tip. We know that our nozzle pressure is 50 because it's a hand line smooth bore. Our friction loss coefficient's 2 times, and then if you look at your chart, our GPMs for 1.25" tip are 328. So 328 divided by 100 squared times 200 feet divided by 100. It's going to give us friction loss of 43 and a pump pressure of 93. Now, we have to combine the 175 GPMs with our 328 from the other line. That's going to give us 503. So while we're figuring those lines separately, when it comes to our supply line, we have to add the volume together to be able to get our friction loss in the supply line. 503, we do not worry about nozzle pressure on the supply line. We just do friction loss only. 3-inch hose is going to be 0.8 times 503 divided by 100 squared times 100 feet over 100. Also, because we have 500, which is more than 350 GPMs, going through this system, and appliance, our gated Y, we're going to have our appliance loss of 10 because it's a small appliance. Our total PDP is going to be our highest line on the skid load, our 171, add our appliance loss, and our friction loss of our supply hose gives us 201. Now, as a pump operator or as another person, you're going to have to man the gated Y or manifold, whichever you're using there, to decrease the pressure on the other line. You're going to have high pressures, 171 obviously on the fog nozzle, 93 on the smooth bore. You don't want to have that much excess pressure on that smooth bore, especially being a 2.5. So here looks a little confusing. It's not so bad. Take it one line at a time. Everything you do, take one line at a time. So we'll start with the top line here. 250 feet, 1.75" hose, 175 GPMs. Nozzle pressure, with it being a fog, is 100. Our friction loss, we're going to do 1.75" hose, so 15.5 times 175 over 100 squared times 250 feet over 100. That's going to give us friction loss of 118 and a total pump pressure of 218. All right, on our skid load, we'll start with the top line. I did correct it on this one. So 100 feet, an 1.75" hose, fog nozzle, 175 GPMs. 100 PSI nozzle. Our friction loss, 1.75", 15.5 times 175 over 100 squared times 100 feet over 100. That gives us a friction loss of 47 adding our nozzle pressure is 147. Middle line, we have 2.5 inch hose, 100 feet, smoothbore 1.1 tip. So 1.1 tip is going to give us 266 GPMs. Our nozzle pressure is going to be 50 because it's a hand line and a smoothbore. Our friction loss coefficient is going to be 2 times 266 over 100 squared times 100 feet over 100. That gives us friction loss of 14 and a total pump pressure for that line of 64. Bottom line, 100 feet of hose, 1.75 smoothbore 15/16 tip. It's going to give us 181 GPMs. So nozzle pressure is going to be 50. Our friction loss, 1.75, 15.5 times 181 over 100 squared times 100 feet over 100. That gives us 52 friction loss and 92 psi pump pressure. So now we have to take and we have to add all of the GPMs out of those three lines. So we have 175 GPMs, 266, and 181. It's going to give us 622 GPMs that are going through that 3-inch hose. Now ask yourself, do we add the appliance loss? Yes, we're over 350 GPMs, so don't forget your appliance loss. All right, so we said 622 GPMs. No nozzle pressures on the supply lines, just friction loss. 3-inch hose is going to be a coefficient of 0.8. So 0.8 times 622 over 100 squared times 200 feet over 100. That gives you 62 friction loss. And of course, you add your 10 for your appliance loss. So as you look at it right this second, and it kind of fell this way when I was making it, I truly didn't do this on purpose. Which line, tell yourself, which line does it look like we're going to have our highest PDP? 218. But once you take your skid load and you add your 147, your highest line, so 147, your appliance 10, and your friction loss is 62, that has a total PDP of 219. Now, you're going to pump these lines, it's the same. It don't matter. But understanding that that pressure is higher than your regular crosslay that you have pulled off, and that's what you're going to pump to is the highest. This one, we have pulled off a 3-inch supply line, so whether it's something that's extremely far off the road, maybe you're using this for brush fires, you don't have a forestry hose and you have to stretch lines extremely far, you're going to use as much supply line as you can to decrease that friction loss and decrease the pressures you have to exceed on your pump. So for this one, 400 feet of 3-inch hose, we used a valve, so we're using a gated Y just because that's what we have on our apparatus anyways. 250 feet, 1.75 hose, fog of 175 GPMs. Nozzle pressure 100. Our friction loss is going to be, it's 1.75, so 15.5 times 175 over 100 squared times 250 feet over 100. And that gives us 118 friction loss, 218 psi pump pressure for that line. Now, because there's only one line, we still have the same GPMs going through the supply hose. So again, no nozzle pressures, only friction loss. 3-inch hose is 0.8 times 175 over 100 squared times 400 feet over 100. That gives us a 10 friction loss. Ask yourself, do we add appliance loss to this? No. It's 175 GPMs. Now, again, as I stated earlier, if your organization says we add 5 psi for anything small appliance and we're flowing under 350 GPMs, add it. Completely fine. So we have a total pump discharge pressure 228 psi. The only way to decrease this, extend your 3-inch hose, decrease the length of your hand line. Now we've taken our deck gun and stretched it into a portable monitor. When we put it on its base, we add hose to it. We're going to have our nozzle pressures, appliance loss. We're even going to have the appliance loss when we are on the top of the apparatus as well. So I said earlier that you have to have account for piping pressure loss. This thing is mounted to a straight pipe into the pump, but it may be elbowed. Also, your deck gun has turns in it too, so you're going to have to add it there. But a ram with a 1-inch tip, this is what's going to throw you off. I didn't have this on that chart, so you're going to have to do some math here. We're going to do 29.7 times your diameter squared. So your diameter squared is 1. So 1 and 1. You're using the diameter of your tip of your nozzle. So 1 squared is 1 times the square root of your nozzle pressure. Your nozzle pressure is 80 psi because it's a smooth bore master string. Your square root of that is 8.94. So you're going to get 265 GPMs out of a 1-inch tip ram. So 265 is what you're going to use on your supply hose. You have 3-inch hose, 650 feet. Coefficient 0.8 times 265 over 100 squared times 650 feet over 100. And that gives you a friction loss of 22.9, so 23, and an appliance loss of 10. Your pump pressure, 113. So 80 nozzle pressure, 10 appliance, 23 friction. Reason I said that earlier about the deck gun having the piping and your pressure losses. So we know that this is piped straight into the pump and from the pump straight into the deck gun. We don't know how the piping is. Again, the only way to truly know and understand is to put gauges where you need them in line. For this, we're going to use, because it's a master string, smooth bore, 80 psi. Then we're going to add our 10, and and that's going to give us 90 psi. Okay, so time for practice. If you want through these, pause after each slide changes, perform your calculations, and then unpause it and let me go over it and see if you got it right. If not, rewind it, try to do it again, figure out where we might have missed something. So if you want, go ahead and pause it and then start it whenever you're done. Okay, so for 3-inch or 300 feet of 2.5-inch hose, smoothbore, 1.25-inch tip, you should have had your nozzle pressure of 50, coefficient 2, times your GPMs of 1.25-inch tip is 328. And then over 100 squared. And then you had 300 feet of hose. Okay. Your total pump discharge pressure should have been 114. Two lines, 150 feet, 1.75-inch hose, smoothbore 7/8 tip. Second line, 250 feet of hose, 2.5-inch. Fog, 250 GPMs. Again, I'm giving you your GPMs. Just use the correct pressures. Pause it if you need to. All right, so for your 150 foot 1.75-inch line, you're gonna have a nozzle pressure 50. For your fog nozzle, it's gonna be 100. Okay. Your top line should have had a friction loss of 60, which gives you a pressure of 110. And your 2.5, your bottom line, should have had a friction loss of 31, which gives you a pump discharge pressure of 131, which you should then have a total pump discharge pressure of 131 psi. Again, highest pressure is going to be 131. You're going to gate your other one down to 110. This is our skid load. Go ahead and pause if you need to. On the top line of the skid load, we have 150 feet, 1.75-inch, smoothbore tip a 1/2 inch. On the bottom, we have 200 feet, a 2.5, smoothbore 1.25-inch tip, supplied by 500 feet of 3-inch hose and a gated Y. Nozzle pressures should be 50s on both. Coefficient 1.75-inch 15.5 times your 1/2 inch tips 52. So 52 divided by 100 squared. It's going to be a very small number. More than likely you're not using this, but again, these are just to make you understand how to be able to perform the calculations. Times 150 feet over 100. Your bottom is going to be coefficient 2 your times, 1.25 tips, 328, so 328 over 100 squared, times 200 feet of hose over 100. With that, now you combined, you have 52 and 328 is your GPMs, 380. That's what's going to be through your 3-inch hose. You have 3-inch hose, 0.8 times 380 over 100 squared times 500 feet over 100. These are the numbers you should have got. So 6 friction loss on the top, 56 pump. On the bottom line, 43 and 83 pump pressure. 10 for your appliance, 57 for your supply. Your total pump discharge pressure is 150 psi. Again, you're going to have to either yourself or have somebody dedicated to the manifold or the gated Y to gate back the 1.75-inch hose so it's not killing the people on the end. This is going to be our ram setup again. So we'll have a nozzle pressure of 80. Our 1.5-inch tip. It's 598. So we're going to have that same 598 flowing through the supply. Our coefficient for 3-inch, 0.8 times 598 over 100 squared times 450 feet over 100. Gives you friction loss of 128, appliance of 10, total PDP 218. So while earlier I discussed for this class, I want you to use 100 PSI for your fog nozzles. Knowing your apparatus is what's key to being a good operator. So yes, being able to perform the calculations appropriately is going to be the best thing. Once you have the ability to do the calculations, now you go out, you see what you have on your apparatus, and you conform your calculations to that apparatus. So yes, while I'm good at doing math and I have the calculations down, they could be wrong now because, as we'll see in just a second, our nozzles could be wrong or different. With our task force tips, you see the picture on the left. That's going to be an automatic flow dual force nozzle. It's going to have a high pressure, low pressure knob. It's inside the bell itself. It also has the readings on the side. That's why I have different pictures to show you where you will find your GPMs, especially on fogs. Your smooth bores, you're either going to have to calculate them and remember them, or some of them are now coming with a diagram on the side that says, hey, it flows this many GPMs. With the task force tips, it's a variable flow nozzle. So it has a spring inside that based on your water flow. So there's a difference in volume and pressure, as we'll see in a couple more exercises in a little bit. You can have all the pressure in the world, but maybe you don't have the volume. Or you may have a lot of volume, you don't have a lot of pressure. As an operator, we'll see how that plays out on our gauges, especially our master intake gauge is where we'll see it at. With this, if you have the switch inside on high pressure or low pressure, that's what the PSI is, the nozzle is going to flow based on your actual water and how much volume you have is what's going to be pushed outside that nozzle. So at 100 psi, it has the capabilities of between 95 and 300 GPMs. At 55 psi, of course, you have to move the dial. It gives you between 95 and 225. It says high pressure, low pressure inside that dial. It's blue and it's red just like it is on the side of this nozzle as well. So when you twist it, you'll know if you're high pressure or low pressure. With these not foam nozzles, they're useful with foam because now it's going to aerate it a little more than your smoothbores are going to, and it's gonna finish it a little more. It's not going to completely finish it like we would with an aerator nozzle or a blower, but it's gonna assist with breaking up the bubbles and expanding a little bit. On the right is going to be a chief nozzle. It's going to be a constant gallonage nozzle. So this one is set, and you can have different rings inside that allows it to flow higher pressure, lower pressure, or well, probably just higher pressure with it being 50, so 75 psi, or it can flow 150 GPMs. It's just different pieces you can put inside. But this one is 175 GPM and 50 psi. And with this one, you may need an aerator to help you finish your foam up. Like I said, while you can do the calculations, knowing your apparatus is the key. Knowing what line has what nozzle on it, figuring out, hey, this is the pump pressure for this line. So if you pull off a hose line, a cross lay at 3 o'clock in the morning, it's 200 feet. You have 175 GPM over 50 psi nozzle on it. Other than elevation loss, you're not going to have to add anything. So it's a constant set pressure line for you. So go out, figure these lines up, every line that you have, work through the calculations, and have them set in your mind. It's all about memorization. Those charts I gave you earlier, it's about memorization. Knowing that 210 GPMs comes out of a 1-inch tip. Knowing that a half-inch tip is going to give you 52 GPMs. Whether maybe you have it, but know your apparatus. These are going to be our larger nozzles. So on the left is going to be our 2.5 fog nozzle. Again, you can see it's different than the 1.75 inch. This one's actually stamped in here. So this one's going to be a 250 GPM at 50 psi nozzle. And then your Elkhart Ram on the right, you can barely see it, just because I was trying to get the entire piece in the picture and the label itself. It's a 500 GPM at 75 psi. So as you can see, while we've been doing the calculations of 100 psi for a fog nozzle, in reality, when we go out to the rig, we're going to have variations. We may have SM30s that do flow at 100 psi. We may have our chief nozzles that flow at 75 or 50 psi. Our Rams that flow at 75 instead of 100. So again, knowing that is extremely vital. These are going to be stack tips. These are going to be your basic stack tips that come on a deck gun. And then, of course, when you pull it off and put it on a base, it's going to be a portable monitor. Our first tip is going to be 1 3/8 tip. Our second tip, 1.5 inches. Our third, 1 3/4 inches. And our fourth is going to be a 2-inch tip. Again, knowing how much water you're needing to flow, how much water you have, and in just a few slides we'll go over understanding our intake drop percentages and how much water we can put out, is determining what you're going to use here. If you need a lot of water, you might unscrew a tip or two. If you need more force, you may narrow it down a little more. Like I said earlier, we had an example of a 1-inch tip on a portable monitor. I have seen apparatus have a 1-inch tip on a portable monitor. That way, when they throw it down, they're only getting those 265 GPMs, but they're putting it hard into the building and deep. One thing I've seen people do, and I figure this diagram may help just a little bit, is understanding where your intakes and your discharges are. For an average sized person, obviously not a giant and not a smaller height disadvantaged height person, from your belly button up is going to be your discharges. From your belly button down is going to be your intakes. I've seen people hook an intake into a discharge. Again, they were newer, they were being rushed on fire scenes, whatever. Because psychologically, even in training, when they're becoming pump operators, I've seen it happen. Because psychologically, it sticks out further, so your mind says, "Hey, this one goes there." So knowing that from your belly button up is your discharges, and your belly button down, that's going to be your intakes. This is a picture of your master intake and your master discharge. As you can see, your from 0 to 400 is red in PSI. So that's how much you're putting out. And if you look in the negatives, so from 0 to negative 30 is red in inches of mercury. We'll go over it in just a second as well, but if you remember, we're trying to overcome our atmospheric pressure. 1 psi raises water 2.3 feet, and then ½ inch of mercury is equal to 1 psi. So with that, that was a lot of information for this one slide, but we're going to get into it. I just want you to understand these are your master intake and master discharges. You may have high pressures on your intakes that may fluctuate your master discharge. So again, don't use your master discharge to actually pump your lines. Pump your lines based on the actual gauge that is attached to that discharge. So some of these, actually I drew this gauge itself. So again, don't try to not make fun of me too bad, but it was very difficult to me, about an hour and a half to draw it, and then I copied and pasted it throughout the rest of the slides. So for our intake drop percentages, if you have a 0 to 10% drop, whatever GPMs you were flowing, not size of line, whatever GPMs you were flowing when that drop occurred, you can pull 3 more of those same lines or same flows. If you have an 11 to a 15% drop, you can provide 2 more of those same flows. If you have a 16 to 25, you can do 1 more. And then if you have a 25% drop or more, you need to try to find some more water. Whether you're going to do tender operations, or you may be in an apartment complex and say, "Hey, we need to go to a main." You know, they could have it gated back inside the complex, but most of the time those are private hydrants. So with those being private hydrants, you may have to go to the main where it's going to be wide open for you. It may be a long way, but you're going to get water. If you don't know how to eyeball and say, "Okay, that was," and I'm going to use easy numbers here and on our examples in a minute, but if you don't know how to eyeball it and say, "Okay, that's about a 5% drop, 10% drop, I can do 3 more of those." The correct formula to figure that percentage is your static. So before you open any lines, what is your static pressure on your intake? Then when you open that line, whatever is left on your intake is going to be your residual. So your static minus your residual times 100. And then divide all that by your original static pressure. So on the bottom there, we started with a static of 150. We subtracted our residual. So when we pulled a valve, we got left with 142 psi. We multiply it times 100, and we divide it by 150. It's going to give us a 5% drop in intake. So this percentage drop is not based on your GPMs. It is on how many more lines of the same size you can add, but your formula is not based on GPMs. It's based on your pressure on your intake. So all these are going to have 150 psi to start with. This is a good example of the last one. Each notch is going to be 25. Each large notch is going to be 25. And each small notch inside is going to be 5. So your 1 3/4 you pull off, you start with a static of 150. You pulled off an 1 3/4 line with 175 GPMs. Now you have a static of 135. Then you're going to multiply that times 100. And then you're going to divide it by your original. So that was exactly a 10% drop on this gauge. Or if you can eyeball it, you could say, hey, 150, I'm at 130-ish. Then, you had 20 pounds. It's roughly 10%. So you could pull 3 lines of the same GPMs for this one. Your next one, you had 150. You had a 2.5 that you pulled off with 328 GPMs. And now you have a residual of 125. So 25 times 100 and then divided by your original 150 is a 16.6, so 17% drop. So based on our chart, you could only pull one more of the same flow. That does not mean that you cannot pull a crosslay with 150 or 175 GPMs. And that's where you would have to do more calculations. So you would have to say, okay, I've got 125, I pull 1 3/4 flowing 175 GPMs, and it drops whatever percentage. Can I pull 2 more of those? That's just something you're going to have to work through. The difference in pressure and volume. You may have pressure, but not the volume. That's why this is indicative of that. So with this one, you're going to have an 1 3/4 with 210 GPMs. You went from 150 PSI to 75 PSI. That is a 50% drop. You need to find more water because there's no way that you're going to be able to afford another drop like that with one more hand line. You would cavitate your pump. So cavitation is when you're introducing air in there because you're pretty much pulling a vacuum inside your pump trying to produce more water. Another thing that you want to look at when you're checking out your intakes is you want to make sure you continually have around 20 psi residual at all times. Whenever you get below 20, now, like I talked about cavitating your pump, there's a probability that you'll start getting into that. So make sure you try to keep a intake of 20 psi and make sure you can understand your percentage drops as to how many more you can pull. I understand it's hard to say, hey, I can't fill that line. But if you don't say that and you charge it, you could cavitate your pump, or you're going to pull pressure and water from your other guys that are inside. Sprinklers. So we have automatic sprinklers and dry pipes, standpipes. The picture on the left, they should be labeled per IFC. They're supposed to be labeled. If not, maybe you need to get with your inspections division or your fire marshal and have them go out there and have a talking. But your automatic sprinklers, that's what we're going to go into and assist. Your dry standpipes, we're actually putting water in there. We're hooking up to the standpipes inside. We're stretching lines to go extinguish the fire. As you can see as well in that picture on the left with the sprinkler, the automatic sprinkler, it has a Storz connector. So what if you don't have hose, which this should not be in your jurisdiction if you do not, but what if you don't have hose that hooks up to that? What if you have 3-inch hose, not 5-inch hose? How can you make this work? We'll go over appliances in a little bit, but you could take a Siamese that goes from threaded to Storz and hook into that directly. Okay. Our dry standpipe system, we'll do some calculations in a few, but you do want to hook both lines up, both sides of that FTC up, so that you can supply. It'll decrease your pump pressure of your apparatus as well. And, you may be higher pressures because you have to go higher floors, but it wouldn't be as bad as if you were just trying to put it all through one line. It does have a clapper valve inside those. That's essentially a Siamese, if you will, on the dry standpipe. It has a clapper valve in there. It will shut off one side so the water won't go in and come out immediately. It does have that clapper valve. But like I said, you do want to be able to feed it with both lines to be able to get more volume and less pressure. In the middle two pictures, those are your OS and Y valves. That's what's going to open and close your sprinkler systems. If the stem is out, that means it's open. If the stem is in, that means it's closed. We want it to be open, so we want the stem out towards us. It has a plunger in there, kind of like on our fire hydrants when they're up and down. It allows this to pull back, and that's why the stem comes out. It's pulling that plunger out and allowing water to flow through. Whereas the bottom, where it's closed, the stem is in, it's clogging the hole, and water's not flowing through. On the right side is a fire pump. So this is what's going to provide pressure to those sprinklers. They do have combination systems where it is a combination of standpipe and sprinkler systems. You're going to have to know this through your pre-plans. You're going to have to know that, I can go straight to that standpipe and hook up because this pump's going to give me the correct pressures. 5 or less sprinkler heads extinguish 90% of fires in sprinkler buildings. And that's given 8 to 15 GPMs per head. They are a good thing. They're not our best friend because we like obviously doing our job, being there to help the people that call us. But they are good for fires that have occurred. Our sprinklers on commercial buildings is you're going to give a pressure of 150 psi. Residential is going to be 100 psi. As you can see in this picture, that's why I posted it. There are buildings that do have systems that have higher pressures. Again, through pre-planning and through signage like this, you're going to know what that system can hold. Obviously, it's a max of 175. You also, through your pre-plans and your standpipe systems, need to know what can that system hold. So if it does have a fire pump, how do you know if you're in the system? Well, fortunately for this little drawing that I made, I'm able to show you. So if you're hooked to a standpipe system or a sprinkler system and it's not flowing appropriately, then you hook into the system. You have to override the pump. The only way to know that you are truly overriding the pump is to look at your intake gauge, not your discharge. You may be discharging what you need to be discharging, but you have not entered the system yet because the pump is still overpowering you. To be able to understand that you're in it, you're going to watch your intake, and as you get closer to the pressures that you need or are supposed to have, with the volume that you're supposed to have, then your needle on your intake is going to drop. That means you are actually putting water from your municipal system through your pump and out the discharge. You had a static pressure because you met the fire pump wall, clapper valve, and then once it entered into the piping to go into the standpipe or sprinkler, it took water from your municipal, and now you have a residual pressure. Standpipes. Relay pumping. This picture looks like an absolute horrible day. Not only is it kind of wet, there's no leaves on the trees, so it's cold. It's a lot of hose on the ground. A big operation. So why do we do relay pumping? Well, long lays, so we need to overcome our pressures of our friction loss. Up large hills, so we need to overcome our elevation loss. We have good volume, but we don't have good pressures. So now we're going to put somebody in there to relay, or if people have seen the four-way valves for hydrants, that you can bring water into the engine, put it back to the four-way to boost the pressure and boost it up to the next apparatus. So remember that when you're doing this, you're going to add a 20 psi. Essentially, you should be giving everything that you have and 20 psi, so that mother truck, the person pumping the fire, can have 20 extra residual at all times. You're not going to give an appliance loss, because they have a pump and they're able to pump water, but you are going to give them that extra 20. So essentially, it's like giving an appliance loss, just 5 psi. For aerials, you're not gonna, without a pump, you will give that 25 psi. So, but if they do not have a pump, if you're pumping straight to an aerial that does have its own pump that is pumping, you're just going to give 20 extra. Tender operations. I'm sure some of y'all will laugh when you see this picture. A tender is a fire apparatus that is drivable with water, not an airplane. An airplane is a tender. A mobile fire apparatus is a tender. I'm sorry, a tanker. The airplane is a tanker. The mobile fire apparatus is a tender. I know, and it's hard to get out of that mindset because of how people have been taught. But when it comes to testing, when it comes to NEMS operations and ICS, knowing what you're calling for and getting what you're calling for is essential. If you call for a tanker and you're on a structure fire and they drop an airplane on top of you, you're going to know it. I don't know if anybody's seen the movie about the Prescott firemen that were killed, but they had an airplane drop on top of them, and that's what it's going to be like. For tender operations, again, we reached to NFPA 1901. That's going to set our minimums, and it's going to say that a tender has to have a minimum of 1,000 gallons on it. There is other appliances and things that it has to have, but it has to have a minimum of 1,000 gallons. And all outlets on it have to be able to produce 90% of that 1,000 GPMs. So it has to be able to produce 900 GPMs to be considered a tender. Nursing is going to be when you have a tender such as this one that's probably 3,000 gallons or more, and you are feeding a supply line to your mother pumper and giving them the water as needed. You're not setting up your dump tanks, you're not drafting, you're just nursing, you're giving them what you have. Maybe you have multiple tenders that are coming in, and they'll fill up their tank on their apparatus. That one gets out of the way, another one comes in, hooks up, and nurses off it too. So do we nurse off 3-inch or do we use 5-inch? We'll do some calculations in a few to help you understand. But if anybody's ever been asked how much water does a 3-inch hose fill or hold, how much water does a 5-inch hose hold? And when we do the calculations, you'll understand that 3-inch hose holds less water than 5-inch hose, obviously because of the diameter. But why is that vital to us? Well, do we want our water being in our hose, or do we want usable water that can go through our pump? So if we have a 50-foot section of 3-inch and it only holds 14 gallons, I'm just throwing a number out there, I'm not saying it's 14 gallons. But a 50-foot section of 3-inch holds 14 gallons, and a 50-foot section, which we don't have, it's 100, but 50-foot section of 5-inch holds 50 gallons. That's 36 usable gallons that was wasted. So, smaller hose, we were able to nurse more water. Drafting. So drafting is where we're going to either use a static water source of some kind, or a lake, a pool, or even our dump tanks. Okay. As I said earlier, it takes 1 psi to raise water 2.3 feet. 1 inch of mercury is equivalent to half of a psi. So if we take atmospheric pressure, which we're trying to overcome, and we multiply it times 2.3 feet, because water raises, or 1 psi raises water 2.3 feet, and we have 14 psi, 14.7. Theoretically, we can raise water 33.81 feet. I know people say don't exceed 20, don't exceed 25. We can raise water 33.81 feet. When you're doing it, you want to make sure you have a hard suction, a strainer, that way you don't get anything into your pump that could mess it up or clog it. You want to have a 24-inch clearance. That way you're not sucking up against something, whether it be a wall or that your strainer is not underwater enough and it keeps coming up or keeps sucking air into your pump, because if you suck air into your pump, you're going to lose your draft. The point of drafting is to make sure that everything is airtight, decrease that pressure in your pump to atmospheric, and then maintain that discharge. Steps to actually getting a draft. Everything's airtight, hard suctions on with a strainer, and it's in the water. So that's going to close that system off. Obviously, you have to open that intake, but no other discharges should be open, no other intake should be open. Your tank to pump should not be open. There is a way to flood it, but that's not, we're going over true drafting. So pump's empty, hard suctions on, strainers on in the water, everything else is airtight. Apparatus is in pump. You're gonna take your apparatus to 1150 to 1250 RPMs, and then you're gonna pull your prime, whether it's pull or you have the air primer. If you have a pump that is under 1,000 GPMs, only use your primer for 30 seconds at a time, and then let it rest for over a minute. If you have a pump that's over 1,000 GPMs, the max you can use it is 45 seconds at a time, and then let it rest. You can burn these up. They do have air primers, and then primers that use oil. So make sure you do have oil in those primers. That's what's going to create your seal to be able to pull, discharge the air, decrease that pump pressure, and then raise your water into your pump. Here's a picture of an operation we actually did at my organization not too long ago. You may have, as you can see, there's a hard suction from the apparatus into one dump tank. So generally you're going to have one dump tank. You're going to be able to bring your tenders in, dump them, they leave, the next one comes in, fills it up, and then it's just a circus really, them coming in and out. So for this operation though, the amount of GPMs we were flowing, the tenders that we had, we set up this dump tank. This is called a dual dump tank operation. If you have two dump tanks of the same size, it doesn't matter which one you draft from. If you have a smaller one and a larger one, the larger one needs to be your fill one. That's so that the tenders can offload and go refill. So maybe you haven't used all your water that's in your larger dump tank yet and send it over into your main draft dump tank. But one of the tenders can come and drop off and then be gone. And you'll understand that when we talk about calculating our time and how many tenders we need in just a second. Right on the left side, the item there is a floating strainer. So that sits on top of the water. It floats, obviously, and suctions the water, and as the water drops, it stays on top of the water and pulls the draft. In the middle, you have your hard suction, and on the right side is your low level strainer. So it's going to be heavy. It's going to be on the bottom, and it's going to pull water in from the sides. And it also has, if you look, it's got an 1 3/4 inlet right there on the front of it. That's a jet siphon. We're going to use this to push water from our secondary dump tank into our primary draft tank. So what you're going to do is you're going to hook an 1 3/4 line up to a discharge. You're going to hook it to that jet siphon on that strainer to a hard suction hose. The hard suction hose is going to go into your primary draft tank, and you are literally creating a huge Venturi effect and pulling that water into the other dump tank. Now, one of the primary things that you need to know for draft operations is you cannot stop flowing water. You cannot get air into your system. Well, having this jet siphon allows you to continually dump water while drafting. You're pulling a draft, you're sending it out, it's just a big circle. If you don't have a jet siphon, or if you're not doing a jet siphon system, things you can do to not waste water, obviously, is put a nozzle on a discharge and flow it right back into your dump tank. If you're not really worried about water, which you should be if you're in a draft operation, dump tank operation, you could take a hose line, stretch it off of your apparatus, and just run it into the grass. Let it flow. Calculating long-term tender operations. You're going to have to figure out what your required fire flow or needed fire flow for the operation is. Again, length times width divided by 3 times percentage of involvement times however many floors. Then you have to calculate the length of time is required for the tender to start dumping its water, leave, fill up, and return to dump again. And that's going to determine how many you need as well. Not just the size of your tenders, but how many you're going to need. So you have a needed fire flow of 200 GPMs. We're going small, easy numbers. It takes a tender 2 minutes to dump, 5 minutes to drive to a fill station, fill hydrant, 5 minutes to fill, and 5 minutes to drive back. What is your total amount of time between dumps? 17 minutes. In that 17 minutes, you could have used 3,400 GPMs. Now, how do we overcome this challenge, if you will? Well, we could use two 2,000 gallon tenders and one 1,000 gallon tender, or we could use one 2,000 gallon tender and 3 1,000 gallon tenders. So I say that to say 5,000. Well, 3,400, 4,000 we could do with. Why not have an extra 1,000 gallons? Because now it puts us to the good 1,600 gallons at a time. That allows us to say, hey, if something in this operation slows us down for whatever reason, we still have 1,600 extra gallons that we can work with. That gives us an extra 8 minutes. Foam. Everybody's seen this eductor on their apparatus. They should. You hook it into your line or onto your discharge directly. You use your dial to set your gauge, and you put your metal rod into your tub and of foam. It creates your venturi, pulls it in at the percentage that it needs to be, and sends it out. What's our uses of it? So we're decreasing our surface tension when we use foam. Some we'll talk about next slide is CAFS operations. It's a little bit different, but still the same. It's using less water and decreasing the surface tension to be able to penetrate into our woods, especially our Class A foam. It's penetrating into there where we won't have rekindles. We don't have to obviously use as much water. Our Class B foams are going to be for our hydrocarbons and our fuels. So it's going to create that layer. It's going to deplete our oxygen, create that barrier, and suppress our fire. Things we should have learned, in Firefighter 2, or if we had a flammable combustible liquids class. Musts that we have to do when we're setting up foam operations: the percentage of your dial, your meter, and the percentage of your foam should match. your nozzle GPMs and your eductor GPMs have to match. You have to have 200 psi at your eductor. So if it's hooked on to your pump discharge, onto your discharge itself, 200 psi right there at your discharge. If it's on, a 50-foot section of 1 3/4 before it goes into the rest of the hose, then you'll have to do your friction loss. But 200 psi has to be at that eductor to create the perfect venturi and create the solution, the mixture that's going down the line. Another must is your nozzle cannot be more than 150 feet from your eductor. CAFs, I said we'd talk about this in the next slide. CAFs is a different beast. So what you're doing here is you're actually introducing air into the system after the discharge, obviously. You're not putting it into your pump. After your pump discharges, then it has a air injection that pushes it down. It's busting up the bubbles even more and finishing your foam. So compressed air foam system, CAFs. A lot of people, or some people I should say, like to use this for fire attack. It wasn't 100% made for fire attack. It was a lot made for overhaul. It can be used for fire attack, but it is more made for overhaul. In the fire attack, you want 5-to-1 ratio, so 5 gallons of solution. Solution is foam and water, so it's already mixed. That's your solution, and then you'll have 1 CFM of air. For overhaul, you have an inverse ratio. You're going to have 1 gallon of solution, 2 CFM of air, up to 5 CFM of air. That's going to allow you to have like that shaving cream. It's going to cover everything, and then it's just going to smother it. It's going to seep in, and again, keep us from going back to rekindles. If you look on the pump panel that I have, you have air injection switches. You have obviously your normal pressure gauges. And then at the bottom of those pressure gauges, you have your GPM meters, your flow meters. So you want to be able, based on fire attack or overhaul, 5-to-1 ratio, or overhaul inverse, 1-to-5, 1-to-2, is what you're going to set your GPMs on. GPMs is your solution. Your system should be set up to accompany how you're going to run your operations. If it gives you 60 CFM all the time on an 1 3/4 line or 1 7/8, whatever you're using, if it's giving you 60 CFM, then you should be flowing 300 GPMs on fire attack. So that's where it comes into play the task force tip nozzles. It may be 100 psi, but it could give you up to 300 GPMs. Well, to meet your 5-to-1, 300 GPMs, 60 CFM of air. The air takes over for your friction loss in your hose. You do not have to figure that. Now, we're going to go into overhaul stage. You can have 12 gallons at a 1-to-5 ratio, 12 gallons of solution, 60 CFM air. That's going to be absolute shaving cream. So maybe you go to 30 GPMs and 60 CFM. The steps for this, you want to make sure you turn your air compressor on at idle. Do not be pumping water and throttled up to turn your air compressor on. It will tear your air compressor up. Then you want to discharge your water foam solution. And then you're going to introduce your air with your air injection switch. Some of these systems now have auto CAF systems. I know Darley specifically has them, where it is running off of your tank water and then the auto calves opens and fills your tank, your onboard water tank. When it gets to a certain level, fills it up, shuts off, depletes it again, or not depletes it completely, but depletes it to that level, opens up, fills it again. So it's not using your hydrant, it's using just your onboard water tank, but it is self-regulating and filling up that water tank as well. Appliances you may need. So on the left is what I call a portable hydrant or a manifold. I use one of these on every fire personally, or when I used to drive and pump. They have a lot of capabilities. You can throw this on the ground after you've laid a supply line or somebody's laid you a supply line, hook it up to your intake supply line, and shut it off. They can send the hydrant whenever they want to. It will not mess up your operations. Then you hook your squirrel tail into it, or a whole section of 5-inch if you need to, and you hook it into your intake and you charge it when you want to. If something happens to your apparatus, you have the capabilities of cutting this off. If, say, you can't even pump, you can't even use your own apparatus as a manifold anymore. Something's happened. You can shut this off, bring another apparatus up there, shut this off, hook to that apparatus, and now it becomes the engine that's pumping. And you never had to touch water supply. If you have a lot of pressure and all your lines are maxed out on your apparatus, you can stretch lines off this. You can have reducers, you can have gate valves, whatever you want, you can put on this and stretch extra lines off of it. The relief valve, which has a little rust knob on it, the relief valve should be pointed towards the hydrant. And most of those relief valves are set somewhere between 125 and 150 psi, completely based on your organization. The valves that turn the water on and off are just like water valves and gas valves. If it's in line, it's open. If it's sideways, it's closed. So you want to make sure when you set this down, you hook it up to the supply line and they're about to charge it, and you'll see why I say that in a second, then it's shut off, and you know it's not going to go shooting off somewhere and hurting somebody, moving your line. 5 inches hard to move once it's charged. So you want to make sure nothing can happen in that aspect. As you can see there's a compartment of appliances. Knowing what's on your apparatus and what you can use, like I said earlier about the automatic sprinkler system, using the Storz. What if you don't have 5-inch hose with Storz connectors? Well, you can use that Siamese right there that is a 2.5-inch coupling. Use your 3-inch hose, hook into that 5-inch Storz connector on the automatic sprinkler, and keep going with operations. What can you make work? So you have to know what you have on your apparatus to even be able to know what you can make work. Remember when I talked about not closing the portable hydrant off or not disconnecting it and them sending water and you weren't ready? This causes a lot of problems and a lot of headache. One, you have a charged hydrant that now you have to turn off. You have a supply line that's not hooked up to your apparatus to be able to use the water efficiently and effectively. You have to figure out how to disconnect that hose and hook it into your apparatus with all the pressure on it as it is. Meanwhile, something is still burning on the other side of your apparatus. So, again, constant communication about water supply and having things in place like the portable hydrant that allows you, hey, send it when you want. I'll take care of the rest when you do. Open drain valves. So these are just your basic discharge drain valves. These are not a main valve, main pump valve. But it doesn't allow the water to fill the hose because it's discharging into the hose and down on the ground out of this drain. So you don't have the capabilities of creating the pressure that you need or the volume that you need getting to the people on the end of the line. If this was a main drain valve, you have the capabilities of draining your pump completely. Now that's where you're going to say, hey, I got a tank to pump. I'm going to use my positive displacement pump with my primer. I'm going to expel that air and everything's good. But when time matters, do you have that time? If you don't have a water supply yet, these drains are open, you could be losing vital water. And of course, if you're on draft, if you are drafting and setting up and everything's airtight except for these drain valves are open, then you won't be able to provide suction because there's air still coming into the system. You're getting correct pressures on your gauges, but your crews are telling you, I need more water or I need more pressure. What could be your problem? Well, if you're getting pressures, that means something is stopping and pushing that water back to your pump gauges and saying, hey, you're getting the right pressures. All right, so from wherever it stopped to the hose or the nozzle is what's keeping them from having the correct pressure or correct volume. Well, kinks. This is why we ensure we do not have kinks in the hose. As an operator, it is your responsibility if you stretch the line to make sure kinks are not there. If they stretch the line and they pull it into the yard and they've created kinks, but they're inside fighting fire, as you're making your laps, as you've gained water supply and you're doing other things, whether it's throwing ladders, stretching other lines, making sure everything's good, whatever it may be, visualize their hose, make sure that they don't have any kinks in their hose. Another big kink that could be an issue, again, this is an intake issue like I talked about earlier, is a kink from the hydrant. Don't get me wrong, I understand everybody's mentality when they see a picture like this that a person shouldn't be parking in front of a hydrant. We have to get water for our people inside. You're doing a disservice to your people inside with this picture right here. Look at the kink in the hose itself as it pushes in the side of the car and then goes up into the window. You're decreasing volume, you're decreasing pressure to your intake. More importantly, you're decreasing the volume that's coming to you. So how do we correct this? Two and a half Storz ball valve. Why can you not hook a 2.5 Storz ball valve onto either side, preferably the right side, towards the back of that car, on that 2.5 discharge of that hydrant, and go around that car to your apparatus? It's not about the fact that they parked in front of a hydrant. We can take care of that problem after, with PD, tickets, conversations. Right now, we need water for our people. So the most important thing is providing that water, the amount of water, the amount of pressure that they need. Maintenance of our apparatus, our pumps. Back flushing, working our TPM, and then running the pump daily and weekly. NFPA says that we are to run the pump weekly, but as operators, we're going to run them daily because we're going to ensure that we know that it works. We're not going to believe in, oh, well, C shift or A shift or B shift ran it. I'm not worried about it. It works. we're going to ensure that it works. What if something happened to that pump, if it froze over in the middle of the night on a call on A shift, you work on B shift, you come in, you don't check it, but A shift did, it didn't freeze over and crack until that night, and now it doesn't work and won't build pressure when you get on a working fire, possible entrapments, exposures, whatever it may be. Back flushing our pump is literally that. We are going to back flush how the pump operates. Water comes in intake, goes out of discharge. What we're going to do is we're going to take that water, hook it to a discharge, and then we're going to flush it out the intake. Our calcium buildup, if water's constantly flowing in one direction, we're creating an opposite direction flow. It could grab pieces of the calcium buildup or sludge or whatever it may be, and then it's going to pull it off and push it out the intake. Our TPM, we're going to work it to make sure it doesn't get stuck. Make sure it works appropriately. Again, a daily thing. Run your pump up while you're making sure your pump works. Crank your TPM to the pressures that you have established through calculations and knowing your apparatus. That, I know my initial tack lines aren't going to be over 110 psi. Work your TPM to 110 psi. Make sure it backs down quarter turn back. On our apparatus days, well, obviously we want to work the TPM all the way open and then all the way closed, just to make sure it has the capability and doesn't create a mind of its own and rust up or calcified up or whatever it may be. Pictures like this right here are the reason that we back flush pumps. And then of course on the left, our TPM working those springs and screws to make sure that they're going to work when we need them to. Some advanced or bonus calculations that I wanted to provide in here for the people that do have to do draft operations. Maybe you want to figure how big your dump tank is that you have and you don't know. This will be a good way to figure it out. So know that there is 1 gallon of water in 231 cubic inches. And then there, in 1 cubic foot, there is 7.5 gallons of water. Okay. There's a difference in these two in the fact that you're going to divide one and multiply the other. So you'll find that your cubic inches that you have and you divide it by 231 is going to give you how many gallons of water it can hold. Whereas your other can so to figure your area of, say, a round swimming pool or any kind of cylinder, you're going to use power squared height. Your R is your radius, which is half of your diameter. So say you have 3-inch hose, your radius is going to be 1.5. So that's 1.5 inches times 1.5 inches. So that's inches squared. Your height, you're going to convert to inches as well. So say you have a 5-foot tall pool. Then it's going to be 60 inches. 5 feet, 12 inches equals 60 inches. So your inches squared times your inches again is going to be inches cubed, cubic inches. That's why you're going to divide 231. Say you have a rectangular pool, Your area is your length times width times your height or your depth, whichever one you want to use. And then times 7.5 gallons of water. So you're finding your cubic feet because length is in feet, width is in feet, height is in feet. Cubic feet. So 1 cubic foot equals 7.5 gallons of water. You multiply it times 7.5. So 1 gallon of water equals how many cubic inches? If you said 231, you're right. When you have hose filled, what shape does it take? A cylinder. So if somebody comes to you and says, hey, how many gallons of water are in a 3-inch line? How many gallons of water are in a 5-inch line? You have the capabilities of performing the calculations and giving them the answer. So area again, pi 3.14 times your radius squared. So we'll use a 3-inch hose is 1.5 times 1.5 and times your height divided by 231. We have 400 feet, a 3-inch hose. Radius is half the diameter, 1.5 inches. Height, 400 feet, we convert it to inches, 4,800 inches. This is what your formula would look like. So how many gallons of water is in 400 feet of 3-inch hose? 146.8 gallons. Here's some more examples, and then we'll get into a couple more practice questions. You're the relay pumper for a fire requiring 713 gallons per minute. What is your total PDP? Again, remember, you are the relay pumper. So you don't worry about nozzles. You don't worry about hoses that they have off. You worry about how many gallons they're flowing, and then what the friction loss is in your hose, plus your 20 residual. So we have coefficient of 5-inch hose is 0.08 times 713 divided by 100 squared times 600 feet over 100. That's going to give you friction loss of 60 and a 20 psi residual for them. So you'll be pumping 80 psi. Now you're pumping an aerial that has a pump. You are relay pumping. You don't worry about height. You worry about how much water they're putting out that 2.5-inch tip, and you worry about your residual. So 2.5-inch tip, if you look at your chart, gives you 1,659 GPMs. Coefficient for 5-inch, 0.08 times 1,659 over 100 squared times 200 over 100. And that gives you friction loss of 44 and your residual of 20 psi. You should be pumping at 64 psi. If you look at your chart, I spoke earlier about the ability to use two lines and how you correct the coefficients. We do not have a coefficient for 5-inch hose. We will in a second use the 3-inch hose, but I want you to get in your mind the two ways that you can use the same hose, the original coefficient, and provide your pump pressures. All right, so there is no pump. You are pumping this. So you will have appliance loss. You do worry about height. You also worry about your nozzle pressure. As we stated earlier, you start with your nozzle pressure, 80 psi, because it's a smooth bore and it's a master string. 2-inch tip, 1062 GPMs. 1062 with two 5-inch hose lines on the ground, you split the volume, 531 GPMs per hose. Now, you're only going to have to figure the calculation one time because they're the same length, they're the same size. But you'll just have to know that both lines are pumped at the same pressures. Coefficient for 5-inch, 0.08 times 531 over 100 squared times 100 feet over 100. Remember, your height is going to be 0.434 times 95 feet. So this is what it should look like. 41 feet for elevation loss, or 41 psi, sorry. 81 for your apparatus, so and 225 for your friction loss in each line. Gives you a total PDP 148. You have a high rise. Reports of fire on the 5th floor of a non-sprinklered high rise. Crews took up 150 feet of 2.5-inch hose, smooth bore, 1.25-inch tip. So what we're going to do here is we're going to use both sides of the chart. I'm going to do it one way, and then we're going to turn around and do it the dual line way with the coefficients and show that they are the same. All right, so for the friction loss for your 2.5 is 32.2. Your nozzle pressure is obviously going to be 50. Your friction loss for the 2.5 is 32.2. In that 2.5 with 1.25-inch tip, you're flowing 328 GPMs. We're going to use our left side of the chart, which is 0.8. And then because we're using that side, we're going to split the volume between the lines. So each line is producing 164 GPMs. So friction loss for the 3-inch hose, 0.8 times split volume, 164 over 100 squared, times 150 over 100. That gives you 3.2 psi. Remember that in just a second. Our elevation loss, we do not count the first floor. So second floor is floor 1. So because it's on the 5th floor, we are only using 4 floors of elevation. In a commercial structure, I want you to use 12 feet for your elevation per floor. So, because we're using 4 floors to get to the 5th floor, 12 feet per floor is 0.434 times 48. Gives us an elevation of 20.8. Our appliance, 25 because it's the standpipe. So nozzle pressure, 50. Then we're going to add all the friction loss together. That's going to be your 2.5 hose and your 3-inch hose. Then we're going to add our elevation, and then we're going to add our appliance. That gives us a total of 148 psi. Now let's use the right side of the chart. Same thing. Reports fire on 5th floor, non-sprinklered, 2.5 with a smooth bore, 1.25 tip. We know that the friction loss for 2.5 is 32.2. Now, because we're using the right side of our right chart and dual lines of 3-inch says the coefficient is 0.2, we continue the volume, the entire volume. We have been able to use the volume because we've decreased our coefficient. So 0.2 times 328 divided by 100 squared times 150 over 100. That gives us 3.2. Remember that number? That's what it was a minute ago. Of course, our elevation loss is still the same, 20.8. Our appliance is still 25. We do the math again, still 148. So it doesn't matter. The only thing that you need to be able to differentiate is which coefficient you're going to use, and do you keep the volume or split the volume. I told you earlier we don't really worry about this, but we will do it just to understand head pressure. Head pressure, we're using an elevated water system on a building, and we need to figure out, hey, this is how much pressure is being given to that sprinkler head. You're going to do it from the water line in the elevated tank to the sprinkler head. So again, I told you commercial structures use 12 feet, and then sprinkler heads are 6 feet below that floor. All right, so the water level in the elevated tank is 22 feet. You're going to drop 2 floors, so that's 24 feet, and then 6 inches. So your head pressure 0.434 times 46.5 feet gives you 20.1 psi. You arrive on scene of a sprinkler activation on the 4th floor. You're pumping 2 lines of 100 feet of 3-inch hose. Remember, we don't have calculations in these because you're pumping the system at 150 psi. Now, you get into longer lays, you may have to start calculating, but you're going to base it off of how many heads you have, how many GPMs it's flowing, and then you'll figure your calculations. But there is minimal friction loss in 100 feet of 3-inch hose. Not enough to matter. Again, too, if you have a pump in the building, you're going to try to get into the system as needed. All right. This is your practice. Again, if you need to pause it, come back to it once you have your numbers, see if they line up with mine. You have fire on the 7th floor. Crew took up 2 1 3/4 hand lines. One of them is 200 feet with a smooth bore 3/4 tip. The other is 200 feet 1 3/4 fog 175/75. All right. With our calculations that we have, we know that we have a 3/4 inch tip providing 118 GPMs and 175 on the fog. That's a total of 293. So we're going to need to put 293 through our 3-inch hose. Our total pump pressures are 169 and 93 for our hand line, so obviously we're going to use a 169. Our elevation is 0.434 times 72, gives us 31. Our appliance loss is 25 for FDC, and our friction loss using the 293 GPMs is 4.25. No matter which way you went, whether it was 0.2 with all the volume or 0.8 split volume. Our total pump pressure should be 229 psi. All right, so practice 7. We have fire on the 3rd floor. Crews took up 150 feet of 2.5 hose line, smooth bore tip, 1/8". Don't pay attention to where those hose lines go into the building. Pretend that they're on the 1st floor. If you need to, pause. All right, so we know that we have a pump pressure, total pump pressure on the line upstairs at 71 psi. We're providing 266 GPMs through the 1/8 tip. Whether we use the left side of the chart or the right side chart with dual lines, we would do 0.8 times 133 over 100 squared times 50 over 100, or we would do 0.2 times 266 over 100 squared times 50 over 100. Either way, you're going to come out with friction loss of 0.7. So like I said earlier, there's minimal friction loss in a short section of 3-inch hose. Now, on longer lathes, we're going to have friction loss, but for 50 to 100 feet, we're going to have minimal. We are flowing through the FDC, so we're going to add 25. And then we don't count the 1st floor. We count 2nd floor and 3rd floor. 12 feet gives us 24 feet times 0.434, elevation loss of 10.4. We have a total pump pressure of 107. Practice number 8. You are the relay pumper for a fire that's flowing a deck gun with a smooth bore of an 1 3/8 tip, 2 1 3/4 hand lines with a fog nozzle of 175/50, so that's going to be 350 GPMs along, and 2.5 hand line with a smooth bore 1 1/4 tip. If you need to, go ahead and pause, figure your math, and remember you are a relay pumper. All right, so we're going to have to add up all the GPMs that are flowing through. Our 1 3/8 tip being 502. Then we have 175, 175 is 350. And then we have the 1 1/4 tip is giving us 328 GPMs, total of 1180 GPMs flowing. Our formula, because we're only going to do friction loss, our formula is 0.08 times 1180 over 100 squared times 800 feet over 100. Now don't forget, we have a 20 residual because we're relay pumping as well. So our friction loss is going to be 89. We're going to give 20 residual. Our PDP is going to be 109. Now you have an aerial. It's 70 foot in the air, 1.5 inch tip, no pump. 200 feet of supply line, 5-inch. Go ahead and pause if you need to. All right, so our nozzle pressure we know is going to be 80. Our elevation is going to be 70 times 0.434. We will have appliance for the apparatus. We're flowing 598 GPMs through our 5-inch hose, so 0.08 times 598 over 100 squared times 200 over 100. So we have 30 elevation, 25 appliance, and 5.7 friction, which gives us 140 psi because you have to include your 80 nozzle. Same scenario with aerial, except for 75 feet in the air, 2-inch tip. It has its own pump. 150 feet, 5-inch hose being supplied by 2 apparatus. Go ahead and pause. All right, so we know we have a 2-inch tip. We do not worry about our elevation because it has its own pump. We are relay pumping this apparatus, this aerial. 2-inch tip gives us 1,062 GPMs. We split the volume and use 0.08. So 0.08 times 531 over 100 squared times 150 over 100. Friction loss of 3 and a residual of 20. Each apparatus has to give that residual of 20. So you would be pumping at 23 psi. Here's your pull. I don't know if you took a picture of the formula earlier. I hope you did. If not, pause, go back and get it real quick. Let's figure out how many gallons are in this pool that we could use for drafting. 40 feet long, 28 feet wide, and 8 feet deep. Go ahead and pause as you need to. $67,200 GPMs in this pool. It's a lot of water. But it's realistic in the fact that if we have motels or pools in people's yards, whatever it may be, even dump tanks, we're not going to have a dump tank this size, but you have the capabilities of figuring out how many gallons a dump tank can hold. That's the most important thing. Like I said before, this class was written to try to pass on information that's been passed on to me, been drilled into my brain throughout the years, and I want to be able to make people comfortable with being behind the wheel and beside the pump panel of an apparatus. I showed you this picture at the very beginning and how, you can carry hose around, you can stretch lines out of the back of a pickup truck, out of the back of a squad or SUV, but that's exactly what you're doing. You don't understand the calculations, the hydraulic side of it. You're not as important as you need to be. So don't just drive hose around. Know your calculations, know how to figure out problems, know how to bypass issues, and become the best driver on your shift, at your station, in your department, whatever it may be. I truly appreciate everybody coming today and listening to the class. I hope that I was able to enlighten people on some ideas or things that they never knew before, show them information that they didn't know. By all means, if you ever have any questions or issues, text me, call me, email me, Facebook, whatever you want to do. I'm always up for questions. So whatever I can do to help, and I look to do some more of these in the future, so I hope that y'all join those too. If you need anything, call me, let me know. Again, thank y'all for coming.